Good morning, folks. This is Todd Coburn of Cal Poly Pomona with lecture 21 of Aero 3271 on the buckling of cylinders and of curved panels. The good news is what we're going to cover today is going to be a baby step forward from what we've already learned, because the methods we're going to use to evaluate the stability of cylinders and curved panels is really the same as what we learned for flat panels. The only difference is that now we will be going to a different curve for buckling coefficients, and also we will be using, in some cases, slightly different variants of the equations. These are some typical cylindrical structures you might run into in aerospace. And we can start by classifying cylinders as short or intermediate, long or very long. Now, short cylinders are going to behave kind of like flat plates, especially when the radius is rather large. Intermediate length will start to see a combination of response that kind of is similar to long cylinders in some cases and similar to short cylinders in some cases. And if our cylinder is long enough, then actually it will fail. The critical failure mode will be Euler column kind of buckling. Cylinders tend to be very stiff, efficient sections because they keep the area far away from the centroidal axis, so they tend to be very resistant to Euler buckling, especially if they're very large cylinders. But the longer they get, the more chance that an Euler column kind of effect will begin to become critical. Now, we're not going to really do anything much different for accounting for these, because the equations that we're going to use will account for whether the cylinder is short, intermediate, or long. However, we will still need to be checking Euler buckling of our column if it looks like that might be critical, because the methods we're going to cover today won't pick up an Euler buckling failure. This is what a typical cylinder looks like if it's loaded in compression or compression with internal pressure. You can see there's a slight difference to the mode shape. And these pictures are out of Brune, since this copy is somewhat bad. Here is the same kind of picture if we have a cylinder subjected to bending. If you look at the leftmost curve, you see that's quite similar to the compression curve. It's just going to be focused on the part of the cylinder that's in compression. And if we have internal pressure, then that will stiffen it and cause the buckles to look a little differently, as you see on the right. So we saw in a couple lectures ago, we investigated the buckling of flat panels, and we used this upper equation for that. If we want to evaluate the buckling of a cylinder, we're going to be using the equation shown here, which looks like it's the exact same form. The only difference is when we had a flat panel, our B dimension was either the short dimension or the loaded dimension. When we have a cylinder loaded in compression, that value is always going to be the length of the cylinder. We can see the rest of this equation looks the same. If we were to go and do a theoretical solution of this equation and of our buckling equation of the cylinder, we would find Kc is equal to this polynomial shown here to the right. We're actually not going to use that, where beta is our half wavelength. And we would find that the K sub c is a function of a number of parameters, and so we would use this z parameter to evaluate what kind of buckling we have. So where with flat panels we basically just look up our K in order to evaluate the compressive buckling strength or critical strength. When we're dealing with a cylinder, we're going to be using this new parameter z, where we're going to calculate the length squared over the radius and thickness times the square root of 1 minus nu squared. This term will be used to classify a lot of our behavior before we go to calculate our k sub c, which for axially loaded cylinders simplifies to this equation shown to the right, 4 square root of 3 over pi squared z. We're actually not going to use that. We're going to go to the curve and calculate our k from those. So whenever we have buckling of a cylinder, we're going to use this equation, the second equation shown on the left. We're going to calculate the z for the cylinder, and then we're going to go to the appropriate curve and get a k. Let's start by the condition where we have no pressure. Whether we have pressure or not doesn't matter. We're going to start by coming to these curves first if we have a cylinder loaded under axial compression. And if we do have pressure, we will then modify our results a little bit. Now, we're first going to take our radius over thickness term, and we're going to find which of these four curves applies. If our R over T is between 100 and 500, we'll use the upper left curve. 500, 1000, upper right, and so on. We'll then calculate the z, which is the L squared over R over T, square root of 1 minus nu squared term. We're going to read the graph for the z. We're going to go up to the lower curve, and we're going to carefully read our k sub c. We're going to ignore the theoretical curve, the upper curve shown for these, and just focus on what's called the design 90% probability design equation curve, which is the lower curve for all these four curves. You're going to need to take care to read this carefully so you get as accurate as a value as you can. Our numbers within the class will tend to float a little bit based on how well you read that curve. I'm going to expect you to show a little bit of due diligence, but obviously, since you're going to be reading this curve, our numbers will differ a little bit and still be in the acceptable range. The hardest part about evaluating the stability allowable for a cylinder loaded in axial compression is reading this log-log curve. It's easy to forget how the log-log curve is read. You need to make sure that by now you know how to read this and you're paying enough attention to read it properly. So if we have a cylinder loaded in the axial compression, if our R over T ratio falls between 100 and 2000, we will read one of these four curves. Now, if it falls outside of that range, we will go to the next curve, which will be shown next. There's a little approach for you. You'll notice this curve is like all the curves from the last slide put together. We aren't going to use this curve at all unless we fall outside of that range, R over T range of 100 to 2000. If we fall between those ranges using the last slide, it will probably give us a value that's easier to read. But if we go outside of those values, if our R over T is smaller than 100 or greater than 2000, we can actually use this curve to try and estimate what the value might be, the best value it would be. Our approach for calculating R over T and then Z and then selecting our curve, reading K sub C and calculating FCR will be the same. If we have a cylinder loaded in bending rather than compression, we're going to use these curves. We're going to take our R over T ratio. We're going to take our L over R ratio. This particular slide shows you both an A basis curve and a B basis curve. So which curve do you think we're going to use? That's right. We're going to use B basis for everything unless I tell you otherwise. Once again, you've got a log-log curve. You're going to take your R over T ratio. You're going to go up to the appropriate L over R ratio and then read what the term is. And instead of being the K, which we were looking at before, this is going to give you the F crit over E. You'll need to multiply the value you get by your E in order to calculate your critical buckling allowable for bending. If we have a cylinder loaded under torsion, then we will use this curve. Here's the equation. Looks like the same exact equation. We're going to calculate your Z, which is the same exact equation for Z. You're going to go read your Z value, read the magnitude of the K for the lower curve, and the sub T is not for tension, K sub T, it's for torsion. Okay? If you have transverse shear, you will read this curve in the same way, but then you will multiply that K that you get by 1.25, and that will be your K for transverse shear. For example, if you had a cylinder loaded in bending with a shear force, then the shear buckling allowable would be calculated as your K from this times 1.25. If you actually have a cylinder in torsion, then actually you read this directly. Now, if we have a cylinder under hydrostatic pressure, we're going to use this curve. What that means is we have a cylinder loaded with some kind of fluid. That would be one way of doing this, which means the hydrostatic pressure is building as a function of the height. That's hydrostatic pressure. If we have a cylinder loaded with uniform pressure, internal or external pressure, then that would just be what we're going to call a pressurized cylinder. But a hydrostatic pressure is one that has a pressure loading that builds as if it were filled with a fluid. If we have that, we're going to use this equation for our F critical that's shown in the upper left. We'll calculate our Z parameter, which sometimes that has that sub L thing on there. Whether it's called Z or ZL, doesn't matter. That's all the same equation. You will read your Z value and then read directly what your K is. And you'll notice at the upper right of the curve you have different values for slightly different R over T squared to 1 minus Poisson's ratio squared terms. One caveat down below, you'll notice that the Poisson's ratio has a little subscript E, which means it's reminding us we're using the elastic value of Poisson's ratio, which is all we ever do, so you can just ignore that little subscript. If we have external pressure, what that means is we have a cylinder being loaded in crush, which means, let's say that you took a cylinder and you put it down in the ocean and your cylinder is relatively small relative to the depth. That would give you a crush pressure of a certain value. If we look down the end of it, it means the pressure is acting like this. You get the same kind of pressure on a rocket where you get a windward and a leeward pressure, which tends to be like this. So you're going to get a larger pressure on one side of it and a smaller pressure on the other side of it. And it's the summation or the integration of those pressures that determine how much shear and crush pressure you have on the structure. So a crush pressure will cause this cylinder to try and buckle like this. A burst pressure will cause the cylinder just to stretch. Obviously, a cylinder will never buckle under a internal pressure acting outward. That's just going to stretch the thing, make it larger and larger as it stretches. But if we have a crush pressure, it can go into the crush buckling mode. Okay, so this is called the cylinders under external pressure, because if we have an external crush pressure on our cylinder, it can buckle, and its buckling will be defined by this equation and this curve. If we have an internal burst pressure, that will tend to stiffen our cylinder for buckling. The stiffening that it performs will be proportional to what we would do for a compression. So if, let's say we have an external crush pressure, if we have that, we're going to go calculate our Z sub L, our Z. Once we have Z, we will read our K for that crush pressure. We'll plug into this equation shown at the upper left, and that will give us our allowable. Now, if we have a burst pressure, we will do the same thing. So for a crush pressure, if we have only crush pressure on a cylinder, we will go calculate our Z. This is just Poisson's ratio. We will use that Z to figure out what our K is. We'll plug that K into this equation to calculate what our FCR is. Our margin of safety would simply be FCR over whatever our crush pressure is, the stress due to that crush pressure, minus 1. Right? Now if we have a burst pressure, then it will never buckle and we won't even calculate this. But if we have a burst pressure and it's coupled with something else that can cause buckling, like torsion or transverse shear or axial load or bending, then we will account for the burst pressure in the same way by calculating a Z, calculating the K, and then what we will do is we'll get the stress ratio due to that pressure, and we will use that to stiffen our cylinder against buckling, and that will be explained on a following slide. Here's a little practice. If your Z is 20, what's your K? If your Z is 12, what's your K? If your Z is 300, what's your K? This is just to help remind you how to read these silly log-log curves. Okay? Now let's say we have multiple loads. If we have multiple loads on our cylinder, we're going to combine those by finding the appropriate interaction equation and the appropriate interaction curve. Stress ratios, we've seen this a few times. These are how we calculate stress ratios. If we have torsion and internal pressure on our cylinder, we're going to use this first equation. If we have transverse shear and internal pressure, we're going to use the second equation. Now what this shows is different interaction equations and the corresponding margin of safety equation. So if we have longitudinal compression and pure bending, we can just add our two stress ratios and use the margin of safety equation shown on the right. If we have longitudinal compression and torsion, like is shown in the first equation, then actually we can use this second margin of safety equation. If we have compression, bending, and torsion, we can use the last margin of safety equation. If we have any of these other combinations, we will need to look and read the interaction curve. If we have tension, we're going to handle it differently. Suppose we have torsion with internal pressure. And let's say we have internal crush pressure. We would go and calculate what our FCR is for the torsion, and then we would calculate what our FCR is for the pressure, whether it's hydrostatic or external. We would then calculate the stress ratio for torsion and the stress ratio for pressure. We would use our two stress ratios in this equation here to calculate our margin of safety. Rewriting that equation, you'll notice we got a little different nomenclature. What this means is, since in this equation here, RC corresponds with RP and RS corresponds with what we're calling RT, we would just plug into this equation. This means 2 over RP plus square root of RP squared plus 4RT squared minus 1. That's our margin of safety equation for this kind of problem. If we have transverse shear with internal pressure, the same exact equation applies, except we're now going to find when we get our KT For torsion, we're going to multiply it by 1.25 to get our K for transverse shear. And then everything else is the same. There's a little more to be said about handling burst pressure. Suppose we have torsion with internal burst pressure, which means we have a cylinder loaded in torsion with a burst pressure. Well, what this means is that we can evaluate our torque, calculate the torsion stress, and we can calculate our FCR for that torsion and calculate our stress ratio for that torsion. We then take our internal pressure. We're going to calculate our stress based on the internal pressure, which in this case is our hoop stress, which is given by PR over T. And we can calculate our allowable for that pressure. We can calculate our stress ratio for that pressure using these two values. It's our F hoop divided by our F critical. However, that F critical is really for a crush pressure, which means in our hoop pressure, because it's based on internal pressure, is actually tensile. Well, tension is a negative compression, so we'll plug a negative sign. What that means is our RP is now going to be negative. When we plug into our margin of safety equation, which was 2 over RP plus square root of RP squared plus 4R torsion squared minus 1. Now what we find is wherever we see this RP, that will now be a negative value because of that negative sign here. What that's going to do is have a stiffening effect, and it's going to increase your margin of safety. So what we see is if we have any kind of loading like torsion coupled with crush pressure, our margin of safety will be smaller than the torsion margin of safety. But if we have that torsion stability margin with a burst pressure, then that burst pressure will cause our margin of safety to be increased relative to what it was just for torsion. We're going to see that some more when we look at our curve panels in a little bit. If we have a curve panel, what is a curve panel? Well, what that means is anytime we have a panel that's not a complete cylinder but it's curved. For example, if we have a fuselage, right, and that fuselage is broken up with the frames and broken up with stringers, we can look at any one of these little panels and see, well, this was our stringer spacing and this value is our frame spacing. That means we have a panel, but this panel is actually curved. We can use the methods of this section to evaluate panels that are curved and have finite dimensions that are not a complete cylinder. If we have a curved panel loaded in axial compression, which means we have a curved panel with some dimension this way and some dimension this way. This is our B dimension, our short dimension, and this is our other dimension, our long dimension. Then we will use this equation and we will calculate the Z for the panel, which means we plug in our short dimension B, our radius of that curved panel, the thickness of that panel, square root of 1 minus Poisson's ratio squared, read our Z, find the appropriate R over T and go to that curve and read a K. Once you have the K, you put it in here with E sub C and everything else, and that will give you your critical buckling allowable for that curved panel if it's acting alone. Now when we have shear, a curved panel loaded in shear like the one shown here, we're going to need to differentiate between what we're going to call a long panel and a wide panel. Okay? If our panel is long, which means the longer dimension is the straight dimension and the shorter dimension is the curved dimension, then we're going to use this curve. If our longer dimension is curved, is the curved one, then we're going to call that a wide panel and use the next graph. So if we have a panel with clamped edges, which means all 4 edges can be assumed as clamped, we're rarely going to have that condition, except maybe analytically. We will calculate our Z. We will then use that Z to calculate a K for whatever A over B ratio we have. We will use that K and the B and the other panel dimensions to calculate our critical buckling allowable. Now if that curved dimension were the long one, we're going to call that a wide panel and use the following curve. Here is the curve we're going to use for wide panels. You'll see our long dimension is now the curved edge. We're calling that a wide panel. We calculate our Z, we calculate our K for the A over B ratio, and plug that K into our equation to get our critical buckling allowable. This curve and the previous one is for clamped edges. When are we going to use clamped edges in industry? Not very often, unless we have a good reason, but you need to be able to do that, analyze that if I ask you to evaluate for a clamped condition. If we have a simply supported edge, this is the condition we will most likely run across. We're going to also have 2 curves. One of them is for what we call a long panel, the other one what we call a wide panel. You're going to calculate your Z, you're going to calculate your A over B, you're going to get your K for that case using the appropriate equation, and then plug in to our critical buckling allowable. If we have external pressure on a cylinder, then we will go back to our cylindrical buckling slides and use that approach to calculate our allowable and stress ratio and margin of safety. If we have a sphere loaded under external pressure, for example, a sphere, which would be like the tanks that propel the second stage engine and those kind of things, then we will use this equation here. So we already saw the equations for cylinders. These are the equations for spheres. We will calculate our Z. Actually, we've got a slight variant of that, because what that's going to do is we're going to have the ability, let's say we had a stiffener on this sphere, like right here, so we only have a partial dome. What this D parameter does, it allows us to account for that. If we have a full sphere, then our D is simply our 2R, and we can just plug that into this equation. So we're going to calculate our Z for the sphere, we're going to calculate our R over T ratio, and then we'll use that to calculate our K. Plug that K into this equation, and that will give us our allowable for the sphere. Got that? So if you have a total sphere loaded in that kind of pressure, then this D will be 2R, own it. And this D will be 2R, right? And this V sub E is simply just Poisson's ratio. Now if we have combined loading, these are the interaction equations that occur. Like let's say we have axial compression or axial loading and shear. If we have axial loading and shear, this is our interaction equation. This is our margin of safety equation. If our axial load is compression, we can just calculate our 2 stress ratios and plug into this equation directly. If our axial load is tension, that will give us a negative RL, because our stress ratio for compression is the compressive stress divided by our F critical for that compression. Both of these should be negative because tension doesn't cause stability failures. However, if we have a tension, what that means is our FC is equal to the negative of the tension. So what that means is this value will be negative now. So our RC will be negative. That means you will plug a negative value in to these two spots, and that tension stress will have an effect of stiffening up or improving your margin of safety for stability. If we have axial load with internal pressure, compression with internal pressure, then this is our interaction equation. Once again, a crush pressure will cause a positive stress ratio. A burst pressure will cause a negative stress ratio. If we have shear with internal pressure, this is our interaction equation. If we have internal pressure on a curved panel, we need to remember that our stress associated with that pressure is a hoop stress. That's going to be the critical stress. If our stress is a burst pressure, what that means is we have a cylinder loaded with a burst pressure, or we have a curved panel loaded with a burst pressure. Both of these cases are going to end up causing tensile hoop stresses, which means this stress will be negative, which means our stress ratio will be FH, and that's going to be negative now over FCR for that pressure. That's how we're going to do it, which we're going to show on this slide momentarily. So we can actually calculate that stress and evaluate the margin of safety that way, or we can calculate this pressure, the critical buckling pressure, as a function of our critical buckling stress. Remembering that this FC for a external pressure will be obtained from the section covering cylinders, not the section covering curved plates, because the cylinder buckling allowables are the ones that are appropriate. Got that? This slide is on general instability. This is not required to be known in this class, but what this is telling us is all of our stability checks so far have been looking locally. We looked at like our stringers. If we look at one of these stringers, and what we're doing is getting a length. Remember, our fuselage looks something like this. We have various frames, and what we're often doing is assuming that the length of our column, our stringer column, is actually the frame spacing. What this is assuming that each of these stiffeners can go into its own buckling between frames. But what if the frame is not stiff enough to provide a pinned condition? If it allows that end of the stiffener to wiggle such that we go into a larger mode shape. What that means is our buckling extends beyond and through the frames. That's what's called general instability, and actually Brune gives a method for evaluating that, which is shown here. So we can see in the first picture where each stiffener, each stringer is supported between the frames. In the second picture, that frame is not sufficient. Brune gives you these equations. When we have bending, external pressure, or torsion, we get three sets of equations for moderate cylinders and long cylinders. Except Brune has a number of typos, which are shown corrected here and in your handbook. We're actually not going to use this at all in this class. You should be aware that general instability is also something that should be checked. This equation actually, while all the other stability modes can be captured in a finite element model, but require a rather detailed finite element model to do correctly, even a rather coarse finite element model will pick up on a general instability problem, and that's usually how this is picked up nowadays rather than using this hand approach, although I have used this and seen it used in industry a few times. Okay? Once again, if you have a copy of Brune, you need to watch out because there's a number of typos in that which have been corrected in your handbook. That's all we have. That's how we handle the buckling of cylinders and curved panels. Enjoy.